G'day Extension 2 students, thank you for joining me. We're going to start this video with a flashback question from the recently published NESA sample exam for Extension 2. We have a sign shown appears on the rear of large vehicles. So you might see this on the back of trucks. If you can't see my mirrors, I can't see you. Which of the four following statements is logically equivalent to this statement? Okay, so which of these four is kind of saying the exact same thing as this? I'll let you pause, read the statements, and take your pick. All right, well done if you selected option B, okay? Because option B is actually what's called the contrapositive of this statement. That's something we looked at in the proof chapter. So we have if this event, if you can't see my mirrors, then I can't see you. Okay, the contrapositive of if A, then B, the contrapositive of that is if not B, then not A. Okay, it's the opposites in reverse is the way I think of it. Option B is the contrapositive because we have I can't see you. The negation of that is I can see you. Then the negation of you can't see my mirrors is you can see my mirrors. Okay, so we've taken the negation of both sort of statements, I suppose, and turned it around. Now, what's interesting about the contrapositive is that every time a statement is true, the contrapositive will also be true, okay? So they are always logically equivalent, okay? As we looked at in a few questions, sometimes the easiest way to prove a statement is to take the contrapositive and prove that, okay? So option B, if I can see you, then you can see my mirrors, is the contrapositive of this statement, which is why they are logically equivalent. So a good trick to look out for. All right, for today's video, at the end of the 3D vectors chapter topic, I want to do a few quick revision questions just to sort of test your skills and see what you know. All right, I've got 3 questions for you. They're all pretty interesting. None of them are easy. And yeah, so here we go. Here is the first one. Again, this is from the recently published sample exam. This is question 10 in the multiple choice, which is usually a pretty tough question. This one's not too bad. Okay, we have 4 pairs of 2D line segments. Okay, so these are line segments, not lines, because as we were looking at before, when you limit the value of the parameter lambda, instead of getting an entire line, you get just a section of a line. All right, we have 4 pairs of line segments. Which pair intersects at exactly 1 point? Go ahead and pause the video, see if you can figure out if any of these are not going to intersect or are going to intersect at more than 1 point, I guess. We're trying to find the only pair of lines that cross at 1 point. All right, so the first thing I'm going to be doing is I'm going to be completely disregarding B and D. Can you look at these two and see why I'm disregarding them as never having to cross over? It's because they are parallel. Okay, remember the first point is just the point that the line is going through. The second is your direction vector. Okay, now these two direction vectors are scalar multiples. If you take this vector, multiply it by 2, you get this one. Okay, and when vectors are the scalar multiples of each other, they have the same direction, which means they are parallel. So these two lines are actually parallel, so they are never going to cross. Same for this one. These two direction vectors, if you take this one and multiply it by -3, you get this one. So they are scalar multiples. So these are both pairs of parallel line segments. Okay, so they're never going to cross. So we're going to get rid of those two. We just got to figure out if it's A or C. Now, typically in 2D, if you have lines that aren't parallel, it means they are going to cross eventually. However, this is not true for line segments. Okay, this is just little pieces of a line, and we're going to see if they cross over. Okay, you can take an algebraic approach if you want. You could say, well, we're trying to find, for the first one, for example, we're trying to find values of lambda such that these two put out the same coordinate. Okay, we're trying to see, is there a coordinate that this line goes through, that this line also goes through? We could do the same thing for these guys, but what you're going to find is that both of these will give a solution, because if you ignore the fact that we are restricting lambda, well, of course, these lines are going to cross because they're not parallel, so they're going to cross over at some point. All right, so an algebraic approach is not going to be super helpful for this one, The way I figured this out is by just doing a very quick sketch of the line segments and just seeing if they cross over. Okay, sketching in 3D is typically very difficult. Sketching in 2D is a piece of cake. Okay, you just got to know that substituting in a value of lambda from 0 to 1 is going to give you a coordinate. All right. So if we look at the first pair, if we look at A, if we think about, so when lambda is equal to 0, what are we going to get? We're going to get 1, 2 plus 0. So we're going to get the coordinate 1, 2, aren't we? All right. When we sub in the endpoint, which is when lambda is 1, we're going to get 1 plus -1, which is 0. And we're going to get 2 plus lambda, which is 5. So we're going to get 0 for the x and 5 for the y, which is this dot here. Okay, so this is the starting point. This is when lambda is 0. This is when lambda is 1. And so this line segment looks like this. All right, we can do the same thing for the second one. We'll let lambda equal 0, and we'll obviously get 3, 1, because we'll get 3, 1 plus nothing. When we let lambda equal to 1, we get 3 plus 1 for our x, which is 4, and we get 1 plus 1, which is 2. So we get 4, 2, which is this point here. Okay, so the value of lambda between 0 and 1 gets us the line from here to here. And there we go. These two line segments are clearly not intersecting. Okay, and so if you got to this point and you're confident that you haven't stuffed up yet, you can say, well, we've proven that A, B, and D are not crossing, so it must be C. And if you want to check, again, you can do a very quick sketch. You can sub in 0 and 1 and get two coordinates, and what do you know? They do cross over. Okay, so that's it. The option was C. And yeah, hopefully that makes sense. If it doesn't, let me know in the comments or send me an email. All right, for the next one. This is from the 2017 VCE. That's the Victorian version of the HSC. This is their specialist maths exam. They do 2 exams. This is from the first one. I don't know if that means it's easier or harder. If you're from Victoria, let me know, because I don't know. We have a 4-mark question, so a fair bit of work. Relative to a fixed origin, the points B, C, and D are defined by the position vectors B, C, and D. Okay, where D has an unknown real constant A. Okay, given that the magnitude of the angle BCD is pi on 3, find the value of A. All right, as always, pause the video, see if you can get an answer or see how far towards an answer you can get, and then I'll tidy up the rest for you. So we're dealing with this scenario here, okay? We have angle BCD, and remember the angle between two vectors is when it's by putting the tails together, so they're pointing this way and this way. We've got CB and CD making an angle of pi on 3. All right, so luckily we have a formula relating the dot product and the magnitude and the angle for a vector. You would have learned that in extension 1. We're going to be applying that here. In order to do that, we need to find expressions for vector CB and vector CD. So that is our first step, okay? Finding the vectors CB and CD. Okay, hopefully if you're an extension 2 student, you know quite easily that to do from C to B, we can just do position vector B, take away position vector C. I probably should have put those as lowercase, but don't tell me. All right, so here's vector B, take away vector C. Okay, we're doing 1 minus 2 for the I component. We're doing minus 1 minus 1 for the J component. And for the K, we're doing 2 minus 1. That works out to be -1 for I. We get 0 for the J, and we get 1 for K. So we just get minus I plus K. All right, so we have no Y value, I suppose. Now for CD, we do something similar. We do position vector D minus position vector C. So subtracting these two, so we're going to get A minus 2 for the I component. We're going to get minus 2 minus 1 for the J component. And for K, we get, well, there's nothing here, so it's 0 minus 1 lot of K here. All right, tidying it up, we get A minus 2 I component minus 1 J component minus 1 K component. All right. So those are our two vectors that are being put together at an angle of pi on 3. So as I mentioned before, we're going to use our formula. I'm just going to write these as ordered triples just to save a bit of space. But these are my two vectors. These are not coordinates, all right? So to use our formula, we're going to use a dot product, okay? Dot product of CB and CD. So we're just multiplying the x components to get minus a minus 2, multiplying the y components to get minus 1, and multiplying the z components to get 0, and summing these three together, okay? So this is the formula that I mentioned. You should know it, but it is on the formula sheet if you're a bit forgetful. We have our dot product equal to the product of the magnitudes multiplied by cosine of the angle between them. So the left-hand side we just did, we've got minus a plus 2 minus 1, so we get minus a plus 1. On the right-hand side, we're doing the magnitudes, so we're squaring and summing and square rooting the components. Okay, hopefully that's pretty clear what I'm doing there. And of course, we've got cos of pi on 3. We already know the angle. We are trying to find A. All right, so if you got this far, that's really all the vectors work done, okay? You've got your concept, you've got your vector logic, basically, you've got your formula. From here on in, we're basically just solving a pretty hectic equation, okay? We're just trying to solve this equation for A, and there is actually a trick to it, which is actually why this is a 4-mark question. This is actually like a little bonus mark at the end, and well done if you can spot it. So first thing we're going to do is we're going to tidy up. So we've got 1 plus 1, so we get square root of 2 for this one here. If we expand this out, we get a squared minus 4a plus 4. I've just got plus 1, and cos of 60 degrees is a half. Okay? What we can do now is we can multiply both sides by 2, so we get rid of that half. So the left-hand side becomes minus 2a plus 2. We can simplify inside this surd here and get a squared minus 4a plus 6. Now we can multiply our two surds together, and we get this. And now we can just square both sides to get rid of this square root term. Okay, so we're going to do a perfect square on the left, expand it all out, and then the hard work's done. Now you just got to collect it all up properly, and you should end up with 2a squared equal to 8, which of course means that a squared is equal to 4. And this is where it gets tricky, because if you say that, well, that means a could be positive or negative 2, you are so close, but that is actually wrong. Okay, it's not positive or negative 2, it's one or the other. See if you can figure out quickly which one it is. Is it positive 2 or is it negative 2? Good place to check to figure this out is any of these lines with the square roots, okay? When you square and get rid of a square root, you kind of lose a bit of what's called generality. So if you take, where's a good place to look? Even if you just go back to the start, okay? Think about if a was positive 2, you'd get negative 2 plus 1. So on the left, you would get negative 1. On the right, you've got a square root times a square root times a half. Okay, and square roots cannot give negative answers. So how could you be doing a square root, multiply with a square root, multiply with a half, and getting a negative answer? It doesn't make sense. Okay, so this left-hand side must be positive, which is why a is negative 2, because then negative a is positive 2, so you get 3 on the left. Okay, so if you didn't check that, if you didn't check your answer and figure out whether it's positive 2 or negative 2, you probably would have only got 3 marks for this. Okay, keeping in mind that I'm not an exam marker, that's just my guess. All right, so positive 2 does not work, negative 2 does work, and our work here is done. That's our answer. All right, one more example for you. Once again, from the recently published sample exam. I really like this question because when I first looked at it, I thought, oh my God, this looks terrifying. It's 4 marks. It's a big, scary picture, and there's a big, scary equation. But actually, if you sort of break this down and just work it piece by piece, this is actually a really nice question, okay? So we have the point A has a position vector of A, B, C. So that's our 3 components. The vector OA makes angles of alpha, beta, and gamma with the x, y, z axes respectively, as shown in the picture, if you can see it. Angle between 3 axes. Okay. Now they give you a big hint here. By taking a dot product with the three unit vectors I, j, and k, prove this equation, that cos squared of all the angles summed together is equal to 1. All right, as always, pause the video, have a go if you want, or if you've got absolutely no idea, which is fair, it's a pretty scary question, and you just want to watch and learn, that's all good. I'm just making some space here. All right, so the key to this question is, once again, this magic formula. Okay, how do I know that? Well, it says right here, by taking a dot product. Okay, here is our dot product formula. Okay, it's got a dot product, it's got an angle, we've got three angles, so this is the golden ticket. Okay, now we're going to do exactly what they said. We're going to take the dot product of vector OA. First of all, we're going to take it with the unit vector I. Okay, we're going to do the dot product of OA with I. Okay, now we can do that because we have the vector OA, it's ABC, and we know what the vector I is, it's 1, 0, 0, isn't it? It's just one unit in the x direction. So if we did this dot product, we would get A times 1 plus 0 plus 0, we would get A as an answer. Okay, that'd be the left-hand side, the dot product. Now we can do the right-hand side. Okay, we can do the magnitude of these two vectors, we can multiply them, and then we can multiply by cosine of the angle, which from the picture is alpha. Okay, hopefully that makes some sense. I'm not going super quick. So left-hand side from doing the actual dot product is just A. Right-hand side with the formula looks like this. Hopefully that's pretty clear. And now luckily the square root of 1 squared is just 1, so we get this. And now we can square both sides to get rid of this square root term here. Okay, so if we square both sides, we get a squared plus b squared plus c squared times cos, that should be a cos squared alpha, pardon me. Do I fix it later? Yeah, I'll fix it later, good enough. Okay, on the left hand side we get a squared, so we can just divide this term underneath, and then we get cos squared alpha equals a squared divided by a squared plus b squared plus c squared. Okay, cool. That is actually most of the hard work done, okay, because the rest is going to be very similar to that. So I want you to think, if this is cos squared alpha, where alpha is the angle between the vector and the x component, I want you to take a wild guess at what cos squared beta is going to look like. Okay, because that's going to be the next part. If you guess it's going to look like this, you are correct. It's going to be the exact same process. The only thing that's going to be different is that on the left-hand side, we'll get a B and not an A. Okay, you can repeat this process again. All right, just make sure you do it correctly, unlike me, and write cos squared alpha, not cos alpha squared. God damn it. But go through this process again, and I promise you, you will get that cos squared beta is b squared over the same denominator. Okay, and again, if you want to do it again with gamma, with the z-axis, you will get that cos squared gamma is equal to c squared over the same denominator, which is so beautiful because now if you sum the three together, which is what the question is asking, sum them together, they all have the same base. So what are you going to end up with? You're going to get a squared plus b squared plus c squared divided by a squared plus b squared plus c squared, which is obviously 1. So it works. It's absolute poetry. All right. So if you are really clever, this 4-mark question can actually be done quite quickly as long as you don't get overwhelmed by the information, don't get too scared by it, and just do what they ask you to. Just take the dot product with the unit vectors and just play around until you get what you need, which you have a target right here. Okay, so we did it. We got the target, so we just chuck on a big fat QED. We are the smartest, quite easily done. And that is the end of the question. All right, hopefully you either found that yourself or at least followed along and it made sense. If not, as always, let me know. And that's the end of today's video. I'm going to skip to the homework for today. Nice, easy one. I just want you guys to relax as it's the end of the term and just make sure you're getting some exercise. Very important to keep active. Very good for your mental health, I find. So that's my recommendation. Keep active and keep learning. Thanks very much for watching, and I'll see you guys in term 2.